Hello, everyone. Welcome to our ME452 final presentation and the analysis and redesign of a manual hand mixer. My name is Aaron Gunn. I'm joined with the rest of Team 28, which is Kimia, Ellie, Tommy, Audrey, and Ben. So a little bit about our product. It is a typical hand mixer, which consists of a crank, which turns the whisks at the end of our product. This tool is used for various applications, including cooking, mixing different matters, or home improvements such as concrete or turning soil. Taking a look at the Amazon analytics, we found that the annual US manual hand mixer demand is about 50,000 devices, with a CAGR of 5.5% in forecast period 2018 to 2028. We assume that consumers of this product are mostly at-home chefs or DIY artisans. Blowing up our assembly, we can see that our product consists of 11 parts, and we will refer to them by name in this convention.
Here is our fast diagram. We have one main branch that relates to homogenizing items with the mixture, and it needs to make contact with the mixture and/or agitate it. We can see in this next slide our functional component mapping matrix. Many components have a role in homogenizing items or maintaining control during use. Looking at our product family design table, we highlighted that our two customer groups have different demands. The type of portability and homogenization may differ between the two. This allowed us to identify which model parts will drive the product differences between the variants, such as the whisk and the whisk base, will have the biggest effect on enhancing portability and agitating the mixture. Here we can see that the different modules provide different functions to meet consumer needs. The addition of the modular mixing attachment allows for different whisks to be attached and used on the mixer. Following the interim report, the bottom design sequence has been fully optimized to assemble the identical parts first and delay differentiation as much as possible.
For design for manual assembly, we analyzed parts that would have a high impact on the total manual assembly time. The whisk base and whisk stem both have a high total manual assembly time, so we chose these parts for our module redesign. The ring gear and gear lever also have a high total manual assembly time. And looking at these four parts, in the quad chart, they all either have high functional importance or high manufacturing and assembly costs, which make them ideal for part consolidation and redesign. The whisk base and whisk stem share the functive of maintain control, while the ring gear and gear lever share the functive of homogenize items. Looking at the whisk base and whisk stem, these parts require press fit while the whisk gears are held in place. They also need to be held in the frame while fastening, which proves handling difficulties. The original total manual assembly time was 30.52 seconds. After part redesign, we consolidated these into one machine part, added a flat for easier set screw fastening, and added a hard stop for the whisk gear placement. This had no effect on the part function, but decreased the manufacturing cost due to smaller machining time and lower tooling cost. This led to an assembly time of 8.45 seconds.
The second part we chose to redesign for manual assembly are the ring gear and gear lever. So before redesign, they required a set screw for fastening, and while they were being assembled together, they would need to be held in place in the frame, and this makes the set screw hole and just generally the fastening hard to access and hard to handle with how small the set screw is. Total manual assembly time with the fastener is 31.5 seconds. After redesign using the guidelines of DFA 2, DFA 3, and DFA 11, we eliminated the use of a set screw by instead adding a snap fit component for the gear and the lever. And to facilitate this part alignment, we created a half circle hole so that turning the crank would also turn the gear. This made no major effect on the part function, but reduces the part lifespan if the snap fit component breaks. And due to the more complex mold and additional machining required for these parts now, the manufacturing costs increased. However, the assembly time decreased to 11.19 seconds. For design for automated assembly, we chose to redesign the ring gear cover, the handle cover, and the frame because they are lightweight and of either high cost or high functional importance. Before redesign, the frame was designed to have the handle covers and ring gear covers press fit, snap fit into the frame, which is unideal and unoptimal for automated assembly. With this, the handling and insertion cost was about 10 cents a part. After redesigning, we followed the guidelines of DFA 1, 6, and 10 in order to eliminate the handle covers, consolidating the frame into one part. We increased the frame symmetry by adding a through hole that was previously only on one side and added a raised wall with a fillet for easier insertion of the ring gear cover. This lowered the assembly cost to about 7 cents a part.
When considering design for manufacturing, the team decided to choose the whisk base and whisk stem mainly because they share the same functive, which was to maintain control. Here you can see the two parts together with all critical dimensions labeled as well as all features called out. When considering process selection for manufacturing, we found that machining would be the most capable process given the material as well as all parameters necessary. So before we redesign our model, we decided to perform an analytical as well as a third-party analysis of the part to see how much it would cost for a batch size of 50,000 parts. The analytical analysis predicted that it would spend about $6.26 per part, whereas a third-party analysis by Hubs.com would estimate around $1.05 per part. It's important to note that our part, before redesigning, showed no errors in DfM Pro when considering the manufacturing process. After redesigning our part, we essentially removed some features that would add extra steps in the manufacturing process, following DFMC guidelines 3, 6, and 15. And this has slightly reduced our costs. Using our analytical method, we saw that a slight reduction in costs, about $6.25, whereas the third-party analysis reduced our cost to about 93 cents per part. Again, here is our new redesigned part with all critical dimensions called out and all features labeled.
So moving on to process selection for our second component, we have the frame, which has since been integrated into the handle covers. The primary functions of this frame are to house components, maintain control of the mixing, and enhance portability. The critical dimensions on all variants of the mixer base are the holes. Their placement and sizing have the tolerance of plus minus 0.25 millimeters, as this is sufficient to ensure the relative packaging of the gears and shafts is smooth. This allows the user to maintain control of the mixing motion. When selecting a process, the two ideal candidates turned out to be the machining and injection molding. However, when considering cost effectiveness from a shipping standpoint, injection molding was ultimately chosen to be superior. Here's the overview of our base before performing DFM with a total cost of $4.55 per unit. The DFM Pro suggestions can be seen in the bottom right corner. And here is the frame with the redesign. DFIM2 was used to keep uniform wall thickness. Notably, the structural supports by the handle were removed due to the implementation of a solid handle, and shaft supports were made to be uniform with the bulk of the material as far as thickness. Furthermore, using DFIM3, draft angles were added where applicable to facilitate part ejection. Finally, using DFIM4, sharp corners were removed to avoid stress concentrations around the handle and gear shaft mounts. This brings the overall cost of the frame down to $4.53.8 per unit. Finally, as you can see, the overall dimensions of the base are unchanged and the critical dimensions and tolerances remain the same from previous.
In addition to making a product that is liked by the consumer, we also want to develop a product service system. Some of the things that we would potentially look into are using recycled materials, providing a standard warranty, creating a book of recipes that are catered towards the use of our hand mixer, and providing other accessories or attachments that one could replace on our device. Here's a summary of our assembly time reduction and cost reduction through our DFA and DFM analysis. The total time reduction was about 19.64 seconds, and the total cost reduction is about 6 cents per part. Some of the positive design highlights of our product include ease of use, portability, and versatility. Some drawbacks of the design include compactness. We believe there's room for improvement to create a smaller product that requires less storage space when not in use. Another drawback would be safety. Due to the nature of the design, the attachments at the end of the hand mixer creates inevitable pinch points. If we were to start the redesign process over again, we would look into potential ways of making the product more compact and safer for the user. Thank you, and that concludes our presentation.